Hello, everybody. Welcome to the DEPONS webinars. This is the first of the DEPON webinar, which is entitled The DEPONS Story, Underwater Noise, Harbour, Porpoise and the Offshore Wind Industry. Today we have a few housekeeping things to run through before we kick off with our speakers. I hope you all can hear me nice and clearly and see my screen. My name is Eloise Burnett. I am Carbon Trust Offshore Wind Manager, and I am going to be the host of today's webinar. Just to run through a few of the functionalities you can use on the webinar, there is a chat function in your user pane on the right-hand side of your screen, which will allow you to ask questions to our speakers. It will also allow you to submit any technical problems to me, and I will do my best to resolve them. So you are aware, the webinar will be recorded today, both the audios and the visuals, and will be shared following the webinar completion time. Also, this is the first of the two webinars we have planned for the DEPONS project and programme. The second one is on the 13th of February at 12 o'clock UK time and is aimed at a more in-depth look at the model update for DEPONS version 2.0. So I encourage you to, if you haven't already, register to that event to get a little more detail from our Aarhus University speaker, Jakob Nob-Nielsen. Right. So to start us off today, we have a short introduction from Jesper Keider-Larsen, who is the team lead of bioscience at Vattenfall. And so without further ado, I will hand over to Jesper. If you have any questions, please make sure you put them in the chat function and we will reach them at the end in our Q&A session, which I will moderate, and we will try and get through as many of your questions as possible. So Jesper, if I could hand over to you, that would be great.
Thanks, Eloise. Welcome also from me on behalf of the DEPONS team and sponsors, on which behalf I've had the pleasure of managing the project. I'm going to briefly introduce you to some basic facts about the DEPONS project and some background on how and why it came about, how it was funded, and why you needn't be too concerned about that. Later, Jakob Nob-Nielsen from Aarhus University will explain the project and go through the main outcome. But before doing so, I'm very pleased that we will have two guest speakers that have kindly offered to help set the scene in terms of underwater noise impacts on marine mammals and individual-based models as a management tool. The former to be provided by Ross Collock from Marine Scotland Science, the latter by Professor Richard Sibley from Bournemouth University. This is quite a day for the DEPONS project. This morning, version 2 of the DEPONS model was released, and being the ultimate end product of the DEPONS project, this means the project has effectively come to its end. The hugely ambitious €2 million research project, conceived more than 6 years ago, has now, by a fantastic effort from Aarhus University, been delivered. And that, to an extent, I would say, exceeding all reasonable expectations for research and software development aiming to break new ground. It has been a great privilege having played a part in this project, and I would like on behalf of the sponsors to take the opportunity to thank Jakob and the team at Aarhus University for their dedication and hard work. You will see the logos of the main sponsors on the slide, all being major energy companies and offshore wind developers. In addition, we were happy to receive minor but very important contributions from Rijkswaterstaat in the Netherlands and the Danish Ministry of Environment. Some background on why and how the project came about. I guess the why is relatively straightforward. When the results of the first studies on the effects of piling of offshore wind farm foundations came out about 10 years ago, it became clear that porpoises were affected at large distances around the construction site during and sometime after the piling activity. With the growing ambitions already then in terms of offshore wind development in the North Sea, this naturally led to increasing concerns about potential cumulative impacts from offshore wind farm construction on the harbour porpoise population. Thus, the need for evidence and tools to help better understand and manage the potential consequences of disturbance caused by piling noise was clear. The how maybe being the more interesting part of the question here, with the inception and funding of a DEPONS project not exactly being the textbook example for projects of this character, scale and level of ambition. Vattenfall, the energy company I'm working for, started the DEPONS project on its own initiative. Having just shown the way developing the first individual-based model for porpoises in inner Danish waters, we had asked Aarhus University what it would take, building a North Sea individual-based model for impacts of disturbance from piling noise, and importantly, one informed by evidence. The research program outlined by Aarhus University overlapping very neatly with key knowledge gaps identified by an independent screening exercise conducted for a UK strategic forum, and having had reassuring noises from various stakeholders consulted, we felt pretty confident we knew what needed to be done, and that if anyone could do it, it would be Aarhus University. Feeling the pressing need for the knowledge, and understanding the considerable time it would take to produce it, we were concerned that attempting to take this project forward in the context of a wider stakeholder collaborative forum, and even more so in light of the cross-boundary perspective, would risk holding this off for too long. We therefore chose to start some of the more critical elements of the project on our own, hoping we would be able to gather the necessary support to realize the full project. Testament, I think, to the need for the knowledge this project aimed to produce, it was eventually possible to secure the full funding, and more so, allowing further expansion of the project collaboratively within the industry. This was fantastic, but of course also potentially a cause of concern in terms of buy-in to the outcome, the project being initiated, fully funded and managed by the industry. We hope that the fact that we have engaged with a reputable university with a lot at stake science-wise, that all results are being published in peer-reviewed scientific journals, and the individual-based model developed, documented to the high standards and made freely available for everyone to use and scrutinize, that this will all go some way in terms of easing any concerns in terms of the outcome being biased. Another thing we did was to invite high-ranking scientists out with the project and experts from national regulators and advisory bodies involved with offshore wind development plans and consenting around the North Sea to join an advisory panel to follow and discuss the developments and preliminary outcomes of the project as it unfolded. On behalf of the sponsors, I would also like to take the opportunity to thank the advisory panel members that offered their time and expertise for the very valuable discussions and input provided during the annual meetings and beyond. That was hugely appreciated. And with that, I will end my presentation.
Thank you very much, Jesper. That was a very useful introduction to the programme. Apologies for those who are experiencing a little bit of dropping in and out of noise there and sound. Hopefully this will improve a little bit as we go forward, as we move through the speakers, which leads me to introduce our next speaker, which is Richard Sibley from the University of Reading, who is a professor at that university. He is going to give a bit more of an introduction to individual-based models, which is the basis of the DEPONS model itself. So without further ado, I'll hand over to Richard, and you should now have control of the slides, Richard.
Thank you. So I've been asked to give a bit of information about the background, the scientific background, and also how the modelling can be used to address management questions. And I'm being especially interested in the case where you want to know how options can deploy on a map. And actually in modelling, the only way to address those management questions is using individual-based models. So I'm trying, Elwaz, to advance my slide, which I don't seem able to do. Can you put it onto the next slide? Yeah, so individual-based modeling comes out of individual-based ecology, and that's been scientifically justified by work by Volker Grimm and Steve Railsback, who wrote this excellent book, Individual-Based Modeling and Ecology. And the premise is that we generally have knowledge and data at the level of the individual. That may come from behavioral ecology, a very well-developed science, but it's about individuals. Or it may come from physiological ecology, and that also works at the level of the individual. So we've got a lot of knowledge and data at the level of the individual, but for these management questions and for scientific questions, we may want to know what happens at the level of the population. And so pretty much the only way to address that, to get from the one level of the individual to that of the population, is to build these individual-based models. And then to simulate what happens in mapped environments. So we take all the knowledge we have about individuals, we model each individual in a big computer simulation, and the individuals together make up the population, and the population dynamics emerge from the computer simulation. So these individuals, they have to have parameters, and their parameters come out of energy budget models. There are various ways to do these energy budget models. I like the straightforward method in terms of parameters such as these, which we're all very familiar with. So that's the method that I have been using. And so now I'm going to take you to two studies. I could have taken, there's an enormous array of studies, but the two I know very well because I've been involved with them. And this one is the elephants of Amboseli. That's Mount Kilimanjaro, you see in the background. And if we go to the next slide, Elwaz, can you help me? It's not moving this time. Oh, there we go. Yeah, so that's Amboseli National Park in the center of the Amboseli ecosystem. And here's the data we get from satellite, which shows the food availability. So down at the bottom here is Kilimanjaro, and the national park is up here. And if I show you what the satellite finds year by year, then, well, it starts off, it's pretty dry now, but now it's greening up after the rains, and now it's intermittent, now it's really green. And you see the satellite data shows us the greenness of the vegetation. And that is what we use. Can we go to the next slide, Elwaz? Right, oh, sorry. Right, so down, we've gone on to, right, so what the individual experiences is shown here. So this is an adult female. The food availability she experiences, that's in the top row in green. And so as a result of eating, when the food's available, she gets into a positive energy balance, shown in the second row in gray. When times are tough, she goes into energy deficit, shown in red here. How she spends the energy is shown in the third row. Here we've got energy. Here we've got in red is what she spends on lactation. That's very major expenditure. Down in gray is basal metabolic rate. So here she's lactating. She gets her first calf through, but you see this second calf, she's run out of energy. She can't go on feeding, suckling the calf, and the calf dies. But she does survive. And so the effects on her body mass are shown at the bottom. Red is what she's spending on, pink is storage, red is lactation. And you see that there in 2010, the years are on the x-axis. In 2010, she ran out of energy and the calf died. So in the next slide, we look at the population consequences. All the individuals are put together in the computer simulation. So here we have population size. The data are in black, data collected by the Amboseli elephant trust over the last 40 years. We only have satellite data since 2000, so that's why the comparison starts in 2000. The best model prediction is shown in dark grey. And so here we've got population size, but there's also the mortalities and the births and so on. And I've also added in here in light grey an indication of the uncertainty in the model predictions. And that comes out of this Bayesian technique, which I like very much because it shows the uncertainty in the model predictions that arises as a result of uncertainty about parameter values. So Vicky went on to use this for management. And so she looked at 6 management options for the Ambercelli ecosystem. So things as they are now, that's top left, that's shown in blue. The worst case where only the current conservation areas remain, that's shown in bottom right. And red shows areas lost to elephants. So Vicky looked at 6 management options, 6 things that may come to pass in the Ambercelli ecosystem. She ran the model for the years up to the end of the century. You see that things persist pretty much as now if the whole ecosystem is available. But in the worst case, scenario F, the population declines by about 75% from current values. So that gives one example of how we can use this approach for management and to explore the effects of different management options. And that this last slide here shows that we did incorporate the likely effects of climate change. There are 40 different climate models. We looked at a range of them in order to see what will be the effects of climate change on Ambercelli, and Ambercelli is lucky that the climate change is not predicted to have much effect on the elephants of Ambercelli. We're now going to turn to a second example of mackerel in the North Atlantic, and so this has been done by Rob Boyd. And so this shows how the simulation model looks on the computer screen. So this is the map. That's top left is Iceland, bottom right is Ireland. The black dots show shoals of mackerel, and the green, the pinkish dots show juveniles, and the green shows the food supply. Again, that comes from satellite. And if we just run the model through, then you see that the mackerel are going down to spawn off the coast of Ireland, and they've spawned now, and they're moving up towards Iceland. And this is the summer feeding season, lots of food up there. Then the dashboard on the right gives you the various things you may wish to know about the stock size and the condition of the fish and so on. So now I'll try and go to the next slide. So this shows that we match the computer outputs to data. Red is the model, grey is the data, and the fit's pretty good, although we probably don't want to stare at that for too long. And then Rob has looked at management implications. He's gone on since this paper was published, but in this paper he looked at the effect of closing off this red square in the North Sea, shown in top right. And the interest is in what's the effect on the stock biomass, the biomass of all the mackerel. And so just look at the light grey and the black line. So if that red triangle is closed, then that's shown by the light grey line. And you see that the stock has pretty much doubled as a result of closing off that square. And so I think that's all that I have. So there's some papers attached to this. So thank you all very much for your attention. And now I'll hand back to the organizer.
Thank you, Richard. That was very useful to give a bit of background into the DEPONS model. Adding to this now is we have got Ross Culloch from Marine Scotland Science, who's a marine mammal scientist, talking about the wider picture of the DEPONS model and looking at kind of the way that offshore wind needs to assess the impacts and population of harbour porpoise and marine mammals. So I'll now hand over to Ross to tell you more about that. Ross, if you could unmute your microphone, we can get going.
Thanks, Eloise. Yeah, perfect. Yeah, just to give a little bit of context as well. So from the perspective of Marine Scotland Science, we give advice to the licensing and operations team here, which are effectively the regulator. So the context of this talk is very much how we can see DEPONS perhaps being useful to inform our decision-making process going forward. So yeah, I was asked to talk a little bit about the concerns and knowledge gaps. So obviously, from this perspective, one of the main issues, or the main issue with marine mammals is pile driving for wind farm development, and that's through impulsive noise. And I'm sure a lot of you will be aware that the way that we assess that is really based on the potential for disturbance, which I always think is important to just note is not necessarily presence or absence in displacement, but we also have to consider things like barrier effects and reduction in foraging efficiency, for example. And then going on to things like physiological injury and temporary and permanent threshold shifts in hearing. Again, a lot of people will be aware of these assessments. And what was raised nicely by Jesper in the initial talk is this interest in frameworks for cumulative impact assessment, which I'll come back to. And although I'll try and avoid making this too Scotland-centric, it'd be a good time to flag up the Scottish Marine Energy Research projects that we develop in Scotland. And these are basically built on receptor groups. So we have a marine mammal specialist receptor group, and these panels basically discuss evidence gaps related to marine mammal ecology and potential impacts of offshore renewables on marine mammals. And although it's Scottish based, I think it's relevant to a lot of other countries too. So although that text is rather small, it's just to give you an idea of what the information is here. I can forward on web links if folk want to see the full table, but this is just highlighting a few of the knowledge gaps here on frameworks for cumulative impact assessment. These are then graded, and you can see potential activity there. For the last one is development of DEPONS for a different species. Right, so yeah, if I talk a little bit more about the idea of cumulative impact assessments from our point of view and what we see as some of the challenges, we're obviously dealing with species that have large management units, home ranges. These span borders, which of course raise a number of potential issues when trying to do cumulative impact assessments. And I think, again, something we see a lot is that we don't just consider wind farm developments. There are other developments, particularly harbour developments, that we need to consider, or as tidal industry starts to take off, things like the Monesto sea kite that you see in the picture there. And another thing that sort of crops up quite regularly is being able to give consideration to changes in piling strategies and flexible approaches to dealing with this. And this also leads into consideration of how to reduce impacts with respects to spatial planning. For example, is it better to have wind farms constructing concurrently or consecutively? And I think that actually feeds into a paper that Jakob and colleagues did that actually tried to address this and did a very good job of doing that. So basically applying the DEPONS model to answering these questions. And again, it actually produces a very good trace document, a transparent and comprehensive model evaluation document, which I think is definitely worth looking at if you're particularly interested in this line of work. So we see the benefits and the potential applications of DEPONS as it being temporally and spatially explicit. That has a lot of benefits to being able to assess potential impacts at a regional scale. And Richard gave a really good overview of individual-based models or agent-based models. That means that you can basically build up your knowledge base from the individual level to give a population-level consequences of disturbance assessment. And at present, DEPONS does represent our best scientific knowledge and effort, which I think ties importantly into that first point, in as much as that's relevant to the data that we have on the spatial and temporal scale that we're extrapolating those data to. It also has the benefit of potentially being used for strategic approach to assessment. So in this case, where limited benefit may be gained from site-specific monitoring, and we've seen some success with this using research advisory groups based on regions within Scotland where wind farm developments have been occurring. And again, these frameworks can be used in EIAs for understanding population level consequences for developments in isolation, and also part of the cumulative impact assessment. Sorry, sticking there. So yeah, I think really when we think about this, if you like, a wish list almost of what we could see with the opportunities and potential future development, then applying the DEPONS framework to other species such as harbour seals, which we're aware that SMRU and colleagues are involved in, Sea Mammal Research Unit. And again, I think we need to highlight, as Jakob does in his paper, that we need more survey data from current regions and for new regions to improve the model. And there are maybe options for doing that through other databases, such as the MERP program that I think has been run by Bangor University, with numerous other universities and institutes involved. We also need to look at getting additional noise recordings of more developments so that we get a better understanding of source levels of pile driving and other activities. And I do think incorporating additional activities such as seismic and tidal turbines into these individual-based models would be extremely useful. And again, we're starting to see more and more tools coming through, if you like, for doing these population consequences of disturbance models, or PVAs. And I think it's important to be able to have these complementary tools in the toolbox, because it's not one size fits all, I think. I think that's me actually. Thanks, Eloise.
Thank you, Ross. That was a really nice overview of the way that a regulatory body and a scientific organisation review offshore wind developments. And so now we're handing over to Jakob Nove Nielsen, who is from Aarhus University, who is the lead scientific contributor and driver of the DEPONS project, and he's a senior researcher at Aarhus University. And he's going to introduce the DEPONS project and the work that they've been doing over the last few years.
Thanks a lot, Eloise. I'll see if I can manage to forward to the next slide. The control panel doesn't really pop up on my screen. Odd. Eloise, could you help me, please? Thanks a lot. Okay. It seemed to have skipped one, but it doesn't matter. I would like to introduce some of the work we have done as part of the DEPONS project, not only the development of the DEPONS model, but what happened? Not only the development of the model itself, but also the huge work we put into gathering the data that was needed to parameterize it as faithfully as possible to make it mimic the porpoise that we see in nature. And there. The objective of the DEPONS project was to develop an individual-based model, and Richard Sibley already talked about what an individual-based model is, and to use it for assessing the population effect of wind farm construction noise on the North Sea Harbour porpoise population. And this kind of model, the individual-based model, Richard already discussed it a little bit, is different from most other frameworks in that it's a bottom-up model based on the processes that drive the population dynamics in nature. And in doing so, it is often producing more realistic predictions whenever you expose animals to, for instance, noise or other kinds of disturbances than classical models do, simply because it directly links to the processes that also influence the animal behavior in nature. So how can I get to the next slide? Thank you. So how does noise and other disturbances affect animals in nature? If you imagine a movement track as seen from above, you might see a porpoise moving through the water happily, and then whenever it encounters food, it starts zigzagging more. It often returns to the places where it has found food and stays there for a while. That's causing it to forage really efficiently on the fish. If you, next please. If a porpoise encounters noise, such as noise from pilot driving, however, it starts being deterred. Next. It starts being deterred and moves away from the noise source. At least that's what we think in most cases. And that obviously causes it to forage less efficiently than if it's staying in the place with a lot of food. It loses energy by moving away. In principle, noise can also directly harm the individual animals, but that can be mitigated by simply deterring them away from the places with the loudest noises, using, for instance, pingers. So you can avoid that, but the loss of energy is something that influences populations. Next slide, please. So the DEPONS model, how does that work? This is a very crude outline of a model that is many thousands of lines of computer code long. If you start in the very top oval up there, the animals, they move through the landscape and use energy. They move just like the animals do in nature. So we have acquired a lot of data to make sure that they do this realistically as in the North Sea. As they move through the landscape, they sometimes find food, and that increases their energy level. So they don't just use energy, they also increase the energy level if they find the food. When they find food in a patch, that reduces the amount of food that's in the patch. So in that way, they compete with the other porpoises that are out there. And then afterwards, when the porpoise has left again, the food gradually recovers, similarly to in nature, and then the patch is available for other porpoises. So the third circle from the top is a certain times of the year, the animals may mate, give birth, lactate, and do other things just like they do in nature. And we have incorporated that in the model based on data from the literature. And on top of that, the different things that they do and encounter influences their energetics. And the animals with low energetics may experience an increased mortality, and also the calves, they die more easily if they have low energetics, just as we believe they do in nature. Next, please. So this, as Richard said, the balance between birth and mortality is an emerging property of the model. So it's something that comes out of the balance between birth and death, just like in nature, making this highly realistic, this framework. Next, please. And you imagine noise influencing the movements of the animals, then it also influences their ability to forage and acquire energy, and in turn the mortality, causing efficiently the carrying capacity of the population to be reduced as a consequence of the noise. Next. But the DEPONS model and the DEPONS project was not just about building the model. There was a lot of data collected. That was a huge effort carried out by a lot of my good colleagues here at Aarhus University. section for marine mammal research. And one of the things we did a lot of the time was to collect data from porpoises on how they move in nature to make sure that we could parameterize the model to mimic real porpoises. Most of the porpoises were handed in from fishermen that caught them in pound nets and then called us to make sure that they were released in good shape. But this happened with a transmitter. Some of them in the North Sea were caught actively also. On the right side of the slide, you can see the movement tracks of animals equipped with the GPS tags. And we found out how they responded to variations in environment. We also have large-scale satellite tracks, and we were able to calibrate the model to reproduce the space use and movements that we found for these animals that were equipped with tags. So we captured all the movements and incorporated them in the model. Next, please. On top of that, to make sure that the animals had a realistic energy intake, we had to find out how the food was distributed. And it's not easy to catch fish, and few surveys have been carried out in the North Sea. So instead, we decided to count the porpoises. The presence of porpoises is a good proxy of food availability, because if porpoises need to forage pretty much all the time to avoid running out of energy and dying. So the areas that are highlighted with dark in the figure to the right are places where a model that we built predicts that the porpoise densities are particularly high, and that shifts over the year. So now we have a movement model that is realistic, and we have a background map for the animals to forage in. Next, please. So on top of simulating the individual animals, the individual porpoises that moved around, we also simulated noise as realistically as possible. And that's something that any user can basically do themselves. It's really easy to adjust in this modeling framework. All you need to supply is where is the piling taking place, what is the source level, and when does it take place in number of ticks. The model works in half-hour time steps. So what time steps are the noise taking place in? And then we'd use, at this moment, fairly simple noise propagation model to model the amount of noise elsewhere. Next, please. So having porpoises and having noise in the landscape, we only need to find out how the animals react to noise in nature. And at the moment, we've done so based on data collected by the Gemini wind park during construction. So what we wanted to find out was how the porpoise densities recovered at different distances from the pilings after the piling noise ended. And to do so, we collected data. Actually, our colleagues from the Gemini wind park did so. They collected data using seapods that record the clicks emitted by porpoises as they navigate through the water and forage and things. So we knew pretty much how many porpoises were in the different parts of this region around the Gemini wind farm during and after construction. Next, please. Then we built a landscape matching this exactly with virtual seapods in it to do the same thing, and calibrated the porpoise's response to specific sound levels to ensure that the porpoise densities recovered in the model just like they did by the Gemini wind park. In Gemini, the response distance in the DEPONS version 2.0, the response distance was a little more than 11 kilometers, so not that long. That was by calibrating the model to make sure that there was a good match between the observed data, which are shown in black, and the simulated recovery of porpoise densities across the different distances from the individual pilings. So this was the best fit we could get, but there's a pretty good fit between that. Next, please. So now we have a model where noise is modeled pretty much as we observed in the North Sea. Movements is modeled the same way, and food acquisition and energy use also. The thing we did now was to build scenarios. We have a picture of a scenario down in the right-hand corner that shows 65 wind farms that are being built in random parts of the North Sea but at realistic water depths. So that's all in all 3,900 piling events. That would be what should be constructed from 2011 to 2020 in order to meet the EU target for renewable energy development. So it's a random scenario, but inspired by what is needed. And the first thing that pops into your mind when you look at this is that the effect of pilings where porpoises respond out to less than 20 kilometers, that's the black and the blue lines, there's nearly no population effect of those pilings. The pink region shows when the pilings take place. And you have to expose the porpoise to much larger noise levels to get an impact of this scenario. If you artificially put it up to 200 kilometers just to try it out, you can see that there's really a big response for a short while, and then the population recovers up to a carrying capacity, at least everything else equal. Next slide, please. So if we kept this highly unrealistic deterrence distance just to see what happened if we changed the piling order to look at the effect of the construction schedule, if that mattered at all, we could see that in the figure to the left shows the figure we had just before, where the wind farms are built in random order, and there's a 2-hour gap between the individual pilings. And the population recovers after just a few years. Actually, just after the final wind farm is constructed, it recovers. If we start building the wind farms in a different order, building the ones in the east first and then the ones in the west, the impact of the noise is much larger. And that is because they lose a memory of how to find their way back to the regions in the east after all these years of continuous piling. Also, if you reduce the lag between the pilings to just 1 hour, so they don't have enough time to come back and keep foraging. They come back pretty fast, but if you keep scaring them away, it influences the population size much more. So construction schedule matters. Maybe not for the short deterrence distances we found by Gemini, but for huge impacts it might. And locally it might really matter. Next, please. And as Jesper already mentioned, all these results have been published, and that's hopefully increasing the acceptance of the modeling framework and the transparency of what we have done to make sure that everything has been tested. We have also produced this trace document that has been made available on GitHub. Please refer to our homepage for further information. And later there will be more papers coming out. Next, please. So to summarize everything, population effects depend on the exact location and timing of disturbances. So you need a modeling framework where the disturbances are spatially explicit, as Ross also pointed out, and that's the case for individual base models. This tool can be used for spatial planning to reduce the impacts of disturbances, also locally. Next, please. We did not find any population effect of the wind farm construction unless we increase the disturbance distances to more than 20 to 50 kilometers. For the realistic distances, there was no impact. Next, please. And this model can be used to assess the cumulative impact of a lot of different kinds of noise, and it's fairly easy to include in the future ships and submarine sonars and seismic survey and that kind of noise. And you may even import it to other regions and even to other species that have similar kind of behavior, as long as we have data on the movements and on where the foraging grounds are. That was the final slide from my side. Thank you. And we're all happy to answer questions now, I think.
Thank you, Jakob. That's great. We have some, first of all, thank you all for listening there, and thank you to our speakers. That was really interesting content. On the screen here, you can see a link to the website, the DEPONS website, as well as contact details for the project lead at Vattenfall of Jesper, Jakob being the scientific contact there with his email address, and myself if you wanted to contact Carbon Trust in any way. If you want to ask any questions, please use the questions tab on your box on the right hand side of your screen. We have got a few questions coming through. So Jakob, the first couple are for you. So if possible, I will ask those to you now. So
Perfect.
In regards to the importance of the construction schedule, so the piling schedule for offshore wind, do you know that the porpoises forget how to find the way back, or do you assume that they forget to find the way back to these areas?
That's a really good question. To some extent, it's something we assume because we can't monitor the individuals close to pile driving locations. We have great difficulties catching animals next to a piling and then monitoring how they move away. All we have is data on the relative abundances, and we assume that by calibrating these things, the patterns that we get out respond to it. But we believe that it's a faithful representation of what's happening on the population size, on the effect on the population at least, because it deters the same amount of animals and it produces a realistic response. But it's something that it would be great to investigate more in the future.
Great. And then again for you, Jakob, could you say anything around the way uncertainty is embedded in the model and how you quantify uncertainty in the results?
Yes. So the main thing that distinguishes the DEPONS model from nearly all the models is that movement is crucial. And we have parameterized the fine scale movements using a correlated random walk and a memory-based behavior that makes them come back to the areas where they've been before, just like in nature. That kind of also answers the previous question. This is taken into account to some extent, the memory. So we made sure to calibrate the movements in the model, not just to take the averages into account, but also the variance observed in the collected data. And the same was the case for the response to noise. So we took everything into account, not just calibrating the means, but all the variances. As for some of the natural history parameters of the porpoises, we did not take it into account. We could do it if it's needed, but the model was not sensitive to those parameters. So we incorporated variability for the parameters that the population size was most sensitive to. Yep, I hope that answers the question.
Great. Yeah, and again for Jakob, would your findings and the model itself be able to be applied to low density areas for porpoises such as the Baltic?
The short answer is yes, it would. So it's not the densities that are tricky, but it comes under some assumptions. It is a model, so it doesn't include everything. So for instance, if contaminants played a very, very important part of the population dynamics in the Baltic, that's clearly not incorporated in the model at the moment. But aside from that, if you assume that they move the same way in the Baltic as in the North Sea, yes, it can be applied.
Great. And then the next question is probably a bit wider. Maybe Jesper, you could give some input on this one as well. What is the likelihood that the reaction distance might get larger as turbines grow in size? So, with currently the 20-50 kilometer reaction distance, is that likely to get larger as our turbines get bigger offshore?
Well, I guess, Louise, I'm probably not the best person to answer that question, but by intuitively, of course, that is what you should expect. But as this model has been developed, and correct me, Jakob, if I'm wrong there, but this is sort of accounted for in the fact that what you put into the model for your simulations is the source level, and as long as you're able to have a reasonably good understanding of the source level of your the piling activity you want to conduct, the model will sort of take account of the increased effect on the porpoises.
Exactly.
Great. I also one here that I was very interested to understand as well. Is the DEPONS model able to explore other potential effects on harbour porpoise, such as climate change, on the population levels?
It is the starting point for such things. We don't know much about the underlying drivers of the population. How is fish responding to climate change? And that's something we need to know more about before we can incorporate it. But the framework is there. You can reduce the amount of fish, so then it's a good starting point for that.
Mm-hmm. Absolutely, yeah. And so I suppose that kind of that fits in the next question really about whether the responses of mobile prey were built into the responses of the mobile prey to piling noise was considered in the model as well.
No, but we would love to do that in the future. Also, we suspect that in some cases the fish may be easier to catch. We have data that suggests that from the North Sea. So when fish are exposed to noise, that may actually make them more catchable. So it could be a better place to forage, in a sense.
Okay. And do you think there is a possibility that the model will be able to calculate cumulative threshold shift and permanent threshold shift at all?
It could easily do that. We haven't included it simply because we thought it's possible in most cases to scare animals away. And in the Gemini wind park, the pingers and the seal scarers were already included as part of the parameterization. And then we don't think that there were any animals left after scaring them away. So, but you could easily, yes.
Mm-hmm. We're having lots of really good questions here. So thank you all for your great input so far. I will continue to get through them as fast as I possibly can. Just one here for you again, Jakob. What is the response time you give to the animals to come back to the area?
Oh, then I should almost move back to that slide. It's in the distance up to 3 kilometers, as far as I remember. They come back after 6 to 8 hours, both around Gemini and in the model. They're actually slightly slower in the model there, but around that, yes.
Great. And in terms of the DEPONS version 2.0, have you carried out any sensitivity analysis on the model?
No, not for that version, but we believe they're pretty similar to DEPONS 1.1.
Okay, and the sensitivity analysis that was carried out in 1.1 was, could you outline how that was undertaken?
Yes, we simply tried to change each individual parameter and see how the population size was changed by changing the parameters. And we also tried to see how the impact of noise influenced the minimum population size experienced during the piling period. And the result of that sensitivity analysis, very briefly, was that the response threshold, the lowest amount of noise that caused a reaction to porpoises, was the parameter that mattered. That was immensely important.
Nice. Yeah, I'm just trying to get through to the next question. So following up on the question about permanent threshold shift, one of the listeners is interested in how the effects of PTS would be parameterized, as in how would it be? Oh, apologies, just got to see the rest of that. How would it be predicted in the model?
Yes, well, we don't know much about whether porpoises are able to catch prey at all if they have PTS, not from nature at least. But we could assume that they can't catch prey at all, or we could reduce that catchability, the ability to catch prey by a certain percentage. So simply put noise of the levels that cause PTS into the model, and then make sure that all the animals exposed to those noise levels, they get PTS. And then afterwards reduce their ability to catch prey. That would be the way to do it, which is not difficult.
Yeah, And then what's the plans for future development of the model? Obviously, you mentioned a little bit in the presentation, but is there any plans to improve the acoustic input into the model and get more kind of acoustic data from other wind farms?
A lot of people have expressed their wishes to have that included, but that clearly depends on the funding opportunities in the future. The DEPONS project, which has funded all this development using all the funding from all the wind farm developers, is finished now. So it's not part of the DEPONS project, but hopefully future projects.
Mm-hmm. Great. And if that was I'm taking a question here from one of the listeners and kind of adding my own spin to it here. So if you did have that pot of gold coming to you right now, Jakob, what would be your number one research priority to fine tune the model and add to it and build it and make it stronger?
Oh, there are many. One of them is, of course, noise. It's not trivial to model noise, and it would be very nice to understand if other noise models would have an impact on the population. We don't know at the moment. We use the spherical spreading model as a start. Prey availability is something that I have a PhD student already working on, and some of the large-scale movement patterns, the things that cause animals to move differently, is very important in relation to one of the questions we had before, whether I was sure that animals could come back to a place where they had been scared away. So we need to understand the drivers of that part a bit more. So that's the three things that are worth looking most at, I think.
Yeah, and I want to encourage all that who are listening now that there are lots of really good questions coming in about the model, and we do have the second webinar for the DEPONS series coming up in early February, and I think it's the 13th of February. So if there are a question in your list that doesn't get answered, please do dial into that second webinar, and Jakob's going to be going into a little more detail about the model and how it works and the thinking behind it. And obviously today it's been quite a brief run through, so that'll be another opportunity for you to ask your quite technical questions to Jakob. But for now, I'm going to ask maybe 3 more questions from the list that we've got here before we close out the webinar. So Jakob, is there an opportunity for the model to include higher sensitivity of calves to underwater noise?
Not at the moment, no, because the calves that are lactating, they're properties of the mother, so they're not modeled explicitly, but it could be done, yes. Maybe I could think of ways to do that, yes. Maybe you can actually, by twisting parameters.
Yeah, bit of food for thought there, I suppose.
Yeah.
And then it's just a fundamental one about apologies, just I feel like I have all the power here picking all these questions, and there's some really, really good ones. So has there been any application of similar models to assess impacts on terrestrial species? Would there be fundamental limitations, or would it largely follow the same principles, do you think?
You could even parameterize DEPONS for certain types of terrestrial species, as long as the movements are fundamentally similar. So if the central place forages, you couldn't use DEPONS. Aside from that, you could. And I do not know of any other model that has ever attempted doing this, include movements and population dynamics in the same model.
Cool. And just to clarify, I suppose it's a question and a clarification, is that the model that are you able to account for the differences in the frequency spectrum for different types of piling? So whether it's a monopile or a jacket foundation, so using pin piles, in addition to the different source levels, is that something that's built into the model?
Not at the moment, no.
Okay, great. All right. with that, I'm conscious that we've come to kind of 1 o'clock end time on this, and I encourage you all to join us in that second webinar to make sure that we can get through some more of these questions and learn a little bit more about the in-depth model version 2.0. This webinar has been recorded, so it is going to be available to share afterwards, and so I'll let you know where you can find that, and you can share that with your colleagues who couldn't make it or have it for record going forward. So all that's left to say is thank you all for joining us today. I hope you found it the webinar really useful. Do get in touch if you have any questions or feedback, and my contact details are on the screen, as well as Jesper's and Jakob's for any specific questions about the project and the scientific input. So thank you all for joining us, and have a good rest of the day.